Okay, today we're going to look at absolute value function transformations. So the first thing we need to do whenever we're looking at transforming graphs is we need to know what the parent function looks like. So our parent function for absolute value is just your basic absolute value of x graph. So if we think about taking the absolute value of all these different numbers, we can get some ordered pairs and start to build our graph over here. So absolute value of 0 is 0, meaning that we would graph the point 0, 0. So that would go here. Absolute value of negative 1 would just be positive 1. So we'd have negative 1, 1, which would be this point here on our graph. The absolute value of 1 is also 1. So that would be the point 1, 1, which you'll notice is just sort of the mirrored point there. We're going to see something similar happen here. For negative 2 and positive 2, our y values are going to be 2. So we will graph the points negative 2, 2, and 2, 2. So that would be both here and here. You should be starting to see sort of what's happening here. And then for our 3's, if we want to continue with that, we would have the point negative 3, 3, and positive 3, 3. And those points would go here, and we should start to see this V shape develop. So the parent function for an absolute value function is going to look like this. It is a V shape. Here at this turning point of the graph, we call that the vertex. That is also the word that goes down here. The turning point of the graph is called the vertex. And that vertex for our parent function is on 0, 0. And then you can see there's a slope of 1 on this side. We just go up 1 over 1, up 1 over 1. And then a slope of negative 1 on this side. We go up 1, left 1, or you're thinking here, down 1, right 1. So this is our parent function. It's really important that we know what it looks like. So if we move on to our next slide, we're going to talk about the different types of shifts that you can have. The first thing we're going to talk about is a vertical shift. So if you add a number to the end of a function, so I've used f of x here instead of absolute value because these are actually true for all types of functions. So you did this some in Math 2 with quadratics, but you can also do this with a square root function or a cubic function or all kinds of different graphs. We're focusing just on absolute value right now. So if I add a number to the end of the equation, that is going to move that equation up or down. And so you can see in this graph here, I just have that parent function. If I put a plus 2 on the end, it takes that whole graph and it moves it up 2 units. You can see that vertex now is at 2 on the y-axis. If I were to put a minus 1 here, it would move that graph down 1. So that's sort of what happens here with our vertical shifts. We're going to have something similar happen with our horizontal shifts. But there's going to be one thing a little bit different here. With the horizontal shift, the number gets added on the inside of the parentheses here. So your independent variable, in this case your x, you're adding to that variable inside of the parentheses. And whenever you do this, the function shifts to the left or right. In the opposite direction. This pen is really lagging. So in the opposite direction. So this is a little bit different. You're adding that number on the inside of the bars. You can see here. But notice right here, I've got my parent function here. Whenever I added 3, which you would think would go to the right because the positive side of the x-axis is over here, the negative side of the x-axis is over here. You would think that should go to the right, but it does not. It actually makes it go to the left 3. Something similar happens over here. If I put a -2, again, you would think that would move it to the negative side, but it does not. It moves it to the right 2. So that's something we must remember whenever we're dealing with horizontal shifts. We're going to move in the opposite direction of what we see. Positives move in the negative direction, and negatives move in the positive or right direction. All right, let's move on to our next one. I'm going to try a different pen here too as well. All right, we can also reflect this graph over the x-axis. So adding a negative sign in front of a function reflects the function over the x-axis. So you can see here we have, again, that same parent function. If I put a negative here, it just flips that function upside down. So it reflects it over that x-axis. And then we have one more type of transformation that we need to look at in this class. There are some others, but they are not covered until some more advanced courses, and that is a vertical dilation. This is going to happen whenever we put a number out in front of our function, so we multiply our absolute value bars by a number. So multiplying a function by a constant, this is a constant, it's just a plain number, causes it to expand or compress vertically. So if you think about taking this graph right here, this y equals the absolute value of x, if you think about taking it and stretching it out taller, so you think about taking it and making the graph, if you grab that y-axis and stretch that out, what you would end up with would be something like this. This would be an expansion by a factor of 2. The graph is twice as tall as it was before. You also notice for absolute values, that slope on the side is 2. You go up 2 over 1, up 2 over 1. If we have a small number here for numbers between 0 and 1, so if we have a fraction here between 0 and 1, we're going to get a compression. So this would be a compression by a factor of 1/2. And whenever we do that, it's going to squish the graph. It's going to make it shorter and fatter here. So let's go on to see what we'll do with some examples here. Alright, so the first thing that we're going to do is just talk about explaining these transformations. We're not actually going to graph them yet, just sort of explain what's happening. So for each of these, we're supposed to describe the transformations that have been performed on the parent graph y equals x. So if I have absolute value of x plus 7, the difference between just the y equals x and the x plus absolute value of x here is that I've got this plus 7. So what I could say here is that the function has been, let's make that, I'll make that shifted up 7 units. Okay. So this would be what we would say for our first example. Now, notice on our second example, our -4 is not on the outside of the bars, but on the inside here. So this is going to be a horizontal shift. It's going to shift left or right, and so we could say the function has been shifted. And in this case, it's going to be right 4 units. We're shifting to the right because we're going the opposite direction when we're on the inside of those bars. Things on the outside of the bars go the direction you think they should go. Inside the bars, you're going to go opposite direction. Our next one has 2 shifts here. So let's give ourselves plenty of room. The function has been shifted. In this case, we would go down 1, and this plus 2 right here is going to be to the left 2 units. Okay, and our last one that we have here that we're supposed to describe actually has 2 transformations. It really doesn't seem like it, but it does. This negative right here is going to be treated separately from the 3. So let's talk about the negative first. So the function has been, and that negative is going to reflect our graph over the x-axis. So reflected over the x-axis. And it will also be transformed by this 3 right here. And that 3 is multiplied by the absolute value bars. So when we multiply by a number, that is a vertical dilation. It means it's going to stretch it out, make it expand it, or it's going to compress it. In this case, since our number is a big number, and I'm going to call anything bigger than 1 a big number, it is going to expand it. So it's going to expand. It's been expanded vertically by a factor of 3. Don't include the negative there. The negative is totally separate. The negative was the reflection, so we only look at just the 3 there for that. So that gives us our answers for these examples. Now let's look at matching some graphs. So this is mostly what you're going to do. We are going to graph a few by hand, but mostly we are going to match graphs in multiple choice style questions. So if we go to the next slide, we just have an example here that says which graph shows f of x equals absolute value of x plus 2 minus 5. So in this case, we need to just think about what's happening with these transformations. We've got 2 things happening here. This plus 2 is a horizontal shift to the left or to the right. Remember, on the inside of the bars, we go the opposite direction. So positive is over here, negative is over here. We're going to go opposite direction, which will be left 2. We also are going to go down 5. So if you kind of think about what like your absolute value would normally look like, it's just the V shape. That needs to go to the left 2 and down 5. 1, 2, 3, 4, 5. So it should look something like this, which is not example A. Here, if we think about taking that absolute value parent function right there and moving it to the left 1, 2, and then down 1, 2, 3, 4, 5, that looks like our vertex would be in the correct spot. So B is looking promising. Let's check over here, down to left 5, definitely not on our graph, so that would not be our answer there. B is correct for this one. Alright, let's move to the next one. Here, we've just got f of x equals 1/3 times the absolute value of x. So we got 3 graphs here, and what I like to do on something like this is I like to think about graphing in just the absolute value of x on each one of these so that I can compare those. Let me actually use a different color here. It's red. So if I graph y equals absolute value of x, vertex would be at 0, 0. That happens for all 3 of these, so that doesn't tell us a lot. And then just plain old absolute value of x would go up 1 to the right 1, up 1 to the right 1, up 1 to the right 1. So you can see here that this is not going to be our answer because this one right here is just absolute value of x. I should probably use a different letter there for this besides f, because we called that f up there. So this is just plain old absolute value of x. That is not the answer. If we look at our second graph, we can see here, when I've got 1/3 right here, that means that we're going to have a compression. Vertical compression by a factor of 1/3. And so that means that my graph is going to be sort of compressed, squished in along that x-axis. It's going to squish it down shorter and fatter. So if I compare that, to that just basic absolute value of x graph, this graph actually looks like a vertical expansion. It looks taller and skinnier, so that is not correct. Over here, this does look squished down, so that's our best answer. We can also see with absolute value bars, that compression factor is going to be the slope of your function, either positive or negative of that number. So like if we look at the right side of this, if I look at the slope, if I go up 1 and to the right 1, 2, 3, right there I am on the graph. So the slope of this side is 1/3. On the other side, it's negative 1/3 because you're decreasing. You go down 1 and to the right 1, 2, 3. But my slope is either positive or negative 1/3 on either side. So that can further confirm that this is the correct answer. All right, let's do one more of these graph problems. We've got absolute value of negative absolute value of x plus 4. So if we think about what is happening here, if we think about the transformations, we have a negative right here, and we have a plus 4 on the inside of our absolute value bar. So that negative is going to be a reflection over the x-axis, which is just a flip upside down. So I am going to mark out B right away because B has not been reflected over the x-axis. So B is not our answer. And then I also have this plus 4 here that is it's on the inside of our absolute value bars. So it's going to move our graph to the left or to the right. So right here, I can see that I have a plus. I'm going to go the opposite direction. So positives on the right, negatives on the left, and I need to go to the left for units. So normally that vertex would be right there at 0, 0. It needs to move to the left 1, 2, 3, 4, which means A is looking like our correct answer. For C, it looks like that vertex has been moved to the right, which is not the correct direction, so it will not be your answer as well. So we are going to do a little more work with graphing these by hand in class tomorrow. So I am not going to do these last few examples. We're going to look at those in class tomorrow.